It was a technical result. Speaking objective, identify in single point. So this is our content and objective. 13 solution introduction solution. What there was a network issue, maybe poor connection. So let's begin again. Ordinary differential equation, CSB 1213, lecture 5. This is our class content, block 4, series solution, unit 13, 14, 15 and 16. We'll be covering for today's class and it will be our class for this subject. Our objective for this class will be understanding and apply power series method to solve a differential equation. Use the Frobenius method. Obtain solution near singular point. Identify ordinary and singular point in differential equation. Identify solve second order differential equation using series technique. Understand and compute Listen tree, polynomial and Bessel function. Apply properties like orthogonality. Find eigenvalue eigenvectors for solving system of ODE. Series solutions is introduction to series solution. What it does is when it's used when differential equation cannot be solved directly. Solution expressed as a power series. Okay. General form consists like y equal to summation n equal to 0 to infinity. A suffix n x to the power n. Now, power series method, what it does is assume solution in series, form, substitute into differential equation, find coefficient recursively. Suppose here is the example. Solve y dash equal to y and solution will be y equal to 1 plus x to the power 2 by 2 factor plus x to the power cube with 3 vector like that and follow solve. Frobenius method. What is Frobenius method? Used when singular point exists. Solution form will be y equal to summation n equal to 0 to infinity a to the a suffix n x to the power n plus r. Earlier it was the same till x to the power n. No, there is no plus r. So r found using initial equation here. So example, Frobenius method, equation x to the power 2x square y double dash plus x y dash minus y equal to 0. Here, what we have to do is assume solution, solve initial equation, then obtain series solution. Then that will be our final solution. Please solve this at home. Unit 14. Moving to Unit 14, series solution of second order. Differential equation. General form will be written as y double dash plus bx y dash plus qxy equal to 0. Use power series when coefficients are function of x. Okay. Next, ordinary versus singular point. So ordinary versus singular point. Ordinary point means functions are analytic. Singular point is not analytic. Types regular singular point and irregular singular point. Okay. Procedure for this ordinary singular point will be assume series solution, substitute into equation, equate coefficient, solve recurrence relation. Next example, this one you solve at home. You solve y double dash minus xy equal to 0. Now we have to assume y equal to summation of a suffix n x to the power n. Find coefficient step by step. Now your work is to find the coefficient step by step. Okay, next moving to our unit 15, Legendre and Bessel function. Okay, now let us know about Legendre function p suffix n x. Solution, this will be the solution. Now your example will be this. Properties of Legendre polynomials will be orthogonal on third bracket minus comma 11. Recurrence relation will be n plus 1 whole bracket p n plus 1 equal to 2s n plus 1 x p n minus n p n minus 1. This will be your recurrence relation in Legendre polynomial. So moving to Bessel function. Bessel function is Jn by x. Jn into x. Solution here for this function will be this. Properties of Bessel function will be oscillatory behavior, recurrence relation, important in cylindrical problem. Example, J0 x, J1 x. Okay. Unit 16. System of linear first order odds. Okay. System of equation will be dx dt equal to ax by by. Now dy dt equal to cx plus dy. You see here ab, first it will come ab and next it will be when dy dt cd will come. The x and y is constant here. Matrix form where dx dt, here it's capital X, then equal to ax, okay, where x equal to x and y matrix. Now in unit 16, eigenvalue and eigenvector for solving system of odds. So let us see one video of how it's solved.
Alright, welcome back. So this is the third lecture on the series of eigenvalues, eigenvectors, and how to solve systems of differential equations. This is one of my absolute favorites because this is where it all comes together. So I'm staying late just for this lecture.
Let's increase the speed.
We have talked about why we have, these systems of ordinary differential equations. X equals ax, x is a vector, a is a matrix, and these dynamics are coupled. But it's a lot easier to solve this system of equations if A was a diagonal matrix. So we try to find a coordinate transformation, some matrix T, some invertible matrix T, it's a single coordinate system Z, so that Z dot equals a diagonal matrix Z, because this is way easier to solve this system where D is diagonal and the dynamics are decoupled than this system here where A is not diagonal.
Join the 9th anniversary. Come build your own pocket city. Turn demos.
And specifically, we derive the eigenvalue-eigenvector equation for the T's and the D's where this is possible. Specifically, A times T equals T times D. This is the eigenvalue. So the coordinate transformation that diagonalizes A are specifically the matrix of eigenvectors of A. And the D, the diagonal system that you get after doing that, these diagonal entries of B are the eigenvalues of A. Good. So I think I want to just show a couple of things. I'm going to do a little bit of Python, MATLAB demonstration here, just to convince you that yes, in fact, D equals, what did I have, T inverse A T is true. And also conversely, that if I had D and T, that A would equal T times D times T inverse. Okay? And it's really easy to compute eigenvalues and eigenvectors in MATLAB and Python, so I'm just going to show you that real quick. And then what I'm going to do, kind of the culmination of this set of lectures, is I'm going to assume that we've gotten A, we've decomposed A into its eigenvectors T and its eigenvalues D. So, however means, Python or MATLAB, we started with A and we solved for T and D. And then I'm going to show you that with those matrices, I can solve my original system of equations up here. So this is like my favorite lecture in differential equations so far. And so I'm just going to show you right now. So the first thing I'm going to do is I'm literally just going to confirm, in fact, that it's easy to get eigenvalues and eigenvectors because I'm going to start in MATLAB. So I'm creating an A matrix 0, 1, -2, -3. And all I'm going to do is get its eigenvectors T and its eigenvalues D using the I command, the built-in I command. So it's literally one line to get all of the eigenvectors and all of the eigenvalues. So I'm just going to run that. And so T, our eigenvector is 1. Okay, so it normalizes them so that they have length 1. So if you take this entry squared plus this entry squared, it'll have length 1, same with this. But essentially you can think of this as the 1, -1 direction. And this is the, I guess it looks like the -1, 2 direction. And what I'm going to confirm for you, and then our eigenvalues are -1 and -2. So I'm going to confirm these two expressions here.
Join the 9th anniversary. Come build your own pocket city. Turn demo skills into city landmark.
So if I take
we'll do fast forward.
the eigenvex.
Join the 9th anniversary. Come build your own pocket city. Turn demo.
We're used to thinking that this is equal to T, D, T inverse. What do I want to do here? I want to tell you that this matrix exponential, sorry, I'm skipping a step here. This matrix exponential e to the A T, and I'm going to drop the under bars.
Okay, so
I told you before that you can take the power series expansion for the exponential e.
it's a 21.51 minute video. So you go through with, in the YouTube solving system of differential eigenvalue and eigenvector for solving a system of ODEs. So you can see by yourself and learn thoroughly if you have any doubt. Okay. Next, let's see the comparison of solution method, use case, and key ideas. So what method we have learned? Power series, Frobenius method, Legendre, Bessel, and matrix method, right? So use case will be in the power series is ordinary point. And in Frobenius method, singular point will be. And key ideas, power series, expand solution, and Frobenius method at exponent R, Legendre, use case, interval, -1 and 1, problems, orthogonal polynomial, key idea, Bessel is cylindrical system, spatial function, key idea, and matrix method, system of orders. Then key idea is eigenvalue. These are the self-assessment question for you to solve by yourself, short questions whichever we have learned in this PPT slides in this lecture. I have given some short question for you to revise by yourself. If you have any doubt, you can email in this email ID given here, or ask your queries in the WhatsApp group as well. So before closing the PPT, let's complete our video. In short, another video I'll be sharing.
X1 equals negative vector 0, 0, 1 times e to the power of 1t, which is
This another video.
the system given by the equation x prime equals a times x, matrix
5 minutes.
A is a 3 by 3 matrix where the first row the entries are 2, negative 5, 0. Second row the entries are 0, 2, 0. And for the third row the entries are negative 1, 4, 1. Recall to use the eigenvalue method to solve the system. The first step is to determine the eigenvalues of matrix A. We do this by setting up the equation, the determinant of the difference of A and lambda I equals 0, and then we solve for lambda. So below we have the setup. To evaluate the determinant, it's best to use row 2 because row 2 has 2 0 entries. The result is the square of the quantity 2 minus lambda times the quantity 1 minus lambda equals 0, giving us eigenvalues of lambda sub 1 equals 1 and lambda sub 2 equals 2. Notice lambda sub 2 equals 2 has multiplicity 2. It may be helpful to write the eigenvalues as lambda sub 1 equals 1 and lambda sub 2 and lambda sub 3 equal 2. The next step is to determine corresponding eigenvectors for each eigenvalue. Recall we do this by setting up the equation, difference of A and lambda I times vector B equals a 0 vector to determine a vector v. Recall, because lambda sub 2 equals 2 has multiplicity 2, if we're not able to determine two linearly independent eigenvectors using this equation, we'll have to follow the procedure outlined. Let's begin with lambda sub 1 equals 1. We begin by setting up the equation for lambda sub 1 equals 1 and simplifying. Now we need to solve this system. I'm going to go and use an augmented matrix. Here we have the augmented matrix for the system. Now we've added in reduced row echelon form, which I've already done here on the right. Notice V3 is a free variable. The first row indicates that V1 equals 0. The second row indicates V2 equals 0. And again, V3 is a free variable. So for example, if we let V3 equal 1, we have the corresponding eigenvector, the vector V1, as the vector 0, 0, 1. This also indicates one independent solution is x1 equals the eigenvector 0, 0, 1 times e to the power of 1t, or just e to the t. And now let's move along to lambda sub 2 equals 2. Again, recall lambda sub 2 equals 2 as multiplicity 2. So again, the first step is to set up the equation and simplify. And now we solve the system using an augmented matrix as before. So here we have the augmented matrix, and here we have the augmented matrix in reduced row echelon form. Again, notice V3 is a free variable. Row 1 indicates that V1 equals negative V3. The second row indicates that V2 equals 0. So if we let V3 equal negative 1, we have the eigenvector V2 equals the vector of 1, 0, negative 1. And therefore, another independent solution is x2 equals the eigenvector 1, 0, negative 1 times e to the power of 2t. At this point, if we try to choose a different V3, we just get a multiple of the eigenvector V2. Therefore, we are not going to be able to determine two linearly independent eigenvectors for the eigenvalue lambda sub 2, which has multiplicity 2, and therefore the eigenvalue lambda equals 2 has a defect of 1. To find a vector V3, another independent solution, we need to set up and solve the equation. The difference of a and lambda I times the vector V3 equals the eigenvector V2. You may want to pause the video and review the notes below. Let's go ahead and set up this equation on the next slide. Again, the equation is the difference of a and lambda I times the vector V3 equals the eigenvector V2. Here we have the setup. Again, notice on the right we don't have the zero vector. For us to find the general solution to the system given by the equation in the form of x prime them, again we use an augmented matrix, which we have here. And now we write the augmented matrix in reduced row echelon form. Again, notice V3 is a free variable. From row 1, we have that V1 equals negative V3 plus 1/5. From row 2, we have V2 equals negative 1/5. And again, V3 is a free variable. So we let V3 equals 0. We have V1 equals 1/5. And V2 equals negative 1/5, giving us the vector V3 is equal to the vector 1/5, negative 1/5, 0. And therefore, x3, which will be a third independent solution, is equal to the sum of the vector V3 and the eigenvector V2 times t, all times e to the power of 2t. And now we have all the information we need to write the general solution. We have the general solution is x of t equals c1 times the eigenvector v1, which is the vector 0, 0, 1, times u to the t, plus c2 times the eigenvector v2, which is the vector 1, 0, negative 1, times u to the 2t, plus c3 times, using the eigenvector v2 and the vector v3, we have the vector v3, which is the vector 1/5, negative 1/5, 0, plus the eigenvector v2, which is the vector 1, 0, negative 1, times t, all times e to the power of 2t. This is the general solution to the given system. I hope you found this helpful.
So we have seen this video, and you can go through by yourself other video which you feel more easy to understand for your practice. And thank you for the class. We'll start the next class after lunch at 2:30 for the course CSB 1214. Thank you. If any doubt, you your queries through WhatsApp group and email.